Hello, I am Sam and this is my lab report for Lab 2, Motion of a Falling Object. The purpose of this lab was to explore the motion of a falling object using experimental and computational models and investigate topics related to net force, acceleration, and terminal velocity. So this lab was successful in creating an experimental model, a computational model that matched well with the experimental model, as well as a theoretical model that also matched well, which predicted decreasing acceleration as velocity increases. So these are my assumptions. We're going to assume that the object is perfectly spherical, that the fluid is incompressible, and that the coefficient of drag is approximately 0.5. And for my experimental model, we have a piece of candy that is dropped, and we have a camera filming against a white background. So the system is the candy and the atmosphere and the ground, and the surroundings is everything else. These are my initial conditions. And here is the theoretical model. So we're going to, we know that the net force is equal to the sum of all forces, which is gravity plus drag. And so we get these equations here, which we can then divide mass to get a acceleration and velocity equation. By the definition of these time derivative, we can get this, and through a U substitution, we can arrive at this differential equation. By solving this differential equation, we can get the equation for the velocity of the object over time, and then by integrating that, we can arrive at an equation for the position of the object over time. So for my recorded video, here it is. And for this video, I first used Tracker to calibrate the distances using an object of known length, and I implemented the X and Y axes. Then I used the Auto Tracker to track the position of the piece of candy over time as it is dropped. So here is my raw data for the position of the candy over time. And here is the graph that I obtained from the data. I then extrapolated the data to find the change in position over change in time, as well as the change in position over time. You can see that the acceleration is relatively chaotic, so then I decided to average the 5 values to get a slightly better system of values. So here is my code. You can see that the constants are initial positions are listed. Delta t is equal to the frame rate, and we have these forces that are acting on the ball. And we also have the drag equation here that is updated every single step, as well as the velocity and the position. So here is the raw data that I obtained for the computational model. I also threw in the theoretical model here from the math equation that we had at the start to just compare it with the other models as well to see if it agrees. So here is the combined graph. You can see that the experimental and computational model, as well as the model of no drag, are relatively close together, while the theoretical model is slightly higher. But if you actually use a smaller step size and get a more accurate computational model, it actually approaches the theoretical model. So all models suggest that as the velocity of the candy increases, the magnitude of its acceleration decreases. The combined graph all demonstrate that the models generally relatively closely agree with one another. The issues we have is that the experimental acceleration data fluctuates significantly, which suggests that Tracker might be relatively inaccurate. It's possibly because of my camera's slow shutter speed causing blurry images, and also that the computational model approaches closer to theoretical model when the step size decreases, which is relatively expected. There's also relatively little difference between the models with no drag and the models with drag, which suggests that maybe it would be interesting to explore this topic over higher velocities that might yield more significant results, or to use an object that has more drag, but there are difficulties surrounding that as well. So the discussion. Which models predict a terminal velocity? That would be the models that include a drag force, in which case the forces will balance out at some case to get the F net of 0, and here we can calculate the terminal velocity here. And you can also see through the computational model that it does that the velocity stops increasing at some point and reaches a certain value. And you can also see the theoretical model agreeing with that as well. You can also see that it confirms the theoretical model just by the fact that it both approaches negative 9.81 t at the start, as well as the terminal velocity at the end. Second, imagine if the object was thrown downward, would the terminal velocity be different? The terminal velocity should be the same because the forced equations have not changed. So we can see here through the computational model that it always approaches the same value. So in conclusion, we can see that we have conducted a lab with a good computational model, a thorough theoretical model, and experimental verification, and that with drag, a ball will experience less acceleration the faster it is, and will eventually have no acceleration when it reaches terminal velocity. So here are my references, and thank you very much for listening.